Aluminum is hard. Let's get that out of the way just at the beginning of this thing. I mean, it's really hard. What can I say? So, most other things inside this factory, you go, you dig up the ore, you smelt it into bars, and you do stuff with it, and you're done. Aluminum is a pain in the, well, it's a late game thing, so I guess it's supposed to be a little trickier. So here we are at sunrise. Oh, I'm in photo mode. Let's get out of photo mode here. It's sunrise and satisfactory, so we've got all satisfactory day to look at this. So what you need to do is you have to have a whole bunch of bauxite coming in, and the bauxite gets turned into with water. You wash the bauxite and you get out alumina solution and you get some silica. I'm going to ignore the alternate recipe that gets you the same thing but no silica and less alumina. So this is the recipe that I like. We are scaled up to 200% here because I wanted to throw a bunch of shards at this and keep the factory small. This is the factory layouts style that I use when I'm working out how to build something. Kind of open. I've got drones. I'm in advanced mode. I've got building without ingredients, so I can just build things and tinker with things and wonder why the heck it isn't working. Anyway, so when I'm building this way, I like to boost my clock speeds, overclock things a bit, and keep the number of buildings small so I can change factories fairly easily. Let's get rid of some of the ingredients that I collected earlier. And I end up with something fairly clean that I can then ponder for a while and then work out how to package up in a nice building. So first step, as I was saying, you bring in the bauxite and the water and you turn out alumina solution and silica. So far, so good. That goes into here where we take the alumina solution and we add coal to it and we turn out aluminum scrap and we get back some water. So we're not getting back a lot of water, but we're getting back some. Specifically, I'm getting back 240 water of the 720 that I use. So I'm getting back about a third of the water I need. So a third of the water these guys need is going to come from here. Cool. So we can take the alumina solution that we got from the right and we can add coal to it and we get scrap out. And notice this number here. I am turning out 720 scrap per minute from this machine. If I overclock this to 250%, that would be 900, which does not fit. My belts are Mark V, and they can handle 780 per minute. So I thought, let's clock this at 200%. And it turns out that if you clock things at 200%, the numbers come out okay for the rest of the factory. When I start pushing really, really hard on this, to try to maximize the amount of things that come out the other end for my ingredients when we go to Megabase. If I ever go to Megabase, I may adjust this, but for now, this is good enough. So you may say, how do I get the water back? The easy way would be just to have a line that takes the water from this guy and delivers it to him, and just one pipe that goes across, boom, 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 and down. And this sort of works, except how do you keep it so that you have enough water coming in from below? This is the original pumped water stage. We come in here. This guy is going to be trying to put as much water in as possible. He's going to fill this guy up with 360, and he's going to fill this guy up with 360, although because we only have 600 coming in, we're going to not quite be able to do that. So if we just put the water in from the right and the water in from the left, it'll fill everybody up and there'll be excess. And the problem is that the excess is probably going to saturate this. If you saturate your fluid loop, this guy won't be able to run because he'll have no place to put things. So, two things here. First, When these two are running, when the Alumina Solution refineries are running, if there's any water coming out of the aluminum scrap, we need to use it. We need to prioritize using the water from the left. As we look at it from here, this is from the left. So we're prioritizing using the water from the left over using the water from the right. So we want to slow down our pumps. Now, I could use valves, and I could say, limit me to 500 meters per second, but what happens if the factory stalls? I want this factory to be resilient to two kinds of stalls. First of all, if we run out of bauxite, and this has happened, I have many drone ports pulling from many places, and I have hit cases where my bauxite was being used by someone else, so I ran out of bauxite. If I run out of bauxite, these refineries will stall, and even if I have limited the rate at which the water can come in from the pump, it doesn't turn it off when the factory stalls. So these guys stall, and this guy happily will fill up the whole thing. So we need what's called a variable input priority pipeline configuration. And there are, you can Google that. It's over in the Satisfactory wiki. What it comes down to is, if you have water coming in low and water coming in from high, the water coming in from low is prioritized. So this refinery will prefer to take water from, never mind. Water coming from high, let's move over to the correct place. Here is our junction here. So we have a valve making sure water can only flow right to left, and a valve here making sure water can only flow left to right. So we know that this guy is not going to be backfilled. Backfill is bad. First guy gets water from below. Boom, boom, we're done. So up to 600 minus 360, so 240 water per minute may flow through here. Or maybe it's going to be 600 per minute because he's stalled. Anyway, we're going to limit that to only flow right to left. I have actually set a valve limit on him just because the valve limit doesn't matter. As I said, if our bauxite dries up, then the water will continue flowing and the rate limit will not do what you think it does. But we're coming in from the top. This guy is still turning out 240 water per minute on the bottom. And we've got a valve here to make sure that nothing from the right is going to backflow, and we don't want his output area to be saturated. Very important. If this pipe right here, this output pipe from this guy, if he ever saturates and this guy can't produce output, if he can't push output, boom, boom, he won't run. If he won't run, these guys can't run. If these guys can't run, they're not going to draw water. If they don't draw water, this guy stays locked. That's a deadlock. So first step is prefer to take from here. So we bring him in low. And the way these vertical junctions work is if you have water from the low side, it will prefer to take it over water from the high side. I don't know if this is a bit of fluid dynamics that coffee stain is going to maintain forever, or if it's a byproduct of a current implementation that's going to go away. But as far as I know, this is the first piece of several pieces that are absolutely required for us to be able to run this thing without locking up. So first step is we take from this guy, and we only take from this guy if we don't have enough. Okay. The other thing is, because this is raised, there's another effect going on here. The pump will fill the first refinery completely before it tries to send anything up over this inverted U-bend. So we actually have two bits of pipeline circuitry going on. So first off, this only fills up if the first refinery is full. So the first refinery will always have water. That's good. And it will drip it down in here only if this pipe is not full. If this pipe is full, it's going to take it all and send it in. We're good. If it's not, We'll take from here. Okay, so what happens when we're stalled? All of this is going to be filled. And this pipe is going to be filled, and there's going to be nowhere to go because it's got filled pipes coming in from the right and a valve here. It's got a filled pipe here and a valve here, so we're full. Now, this guy's full. It turns out some output. So it turns out some alumina solution and silica. Boom. And he turns out some alumina solution and silica. Boom. And this is all full. So he's got alumina solution, and he's got coal coming in. And he turns out some scrap, and he turns out some water. So we could still have a situation where this would deadlock, but instead I put another fork here, and we send water over to a buffer area and a big U-bend, so we only fill this up as a last resort. Now this doesn't need to be this high. I put it this high because I was worried that we may be, I would prefer to fill up from this guy, I would prefer to fill up this area here from me, okay, before sending it on. But if we really do saturate, this is going to pump through here, and this is within the head lift of the refinery. Got to pump through here, and we're going to go into the fluid buffer. Notice the fluid buffer doesn't have a whole lot of water in it. We're currently stalled. Currently stalled because we have no place to put our output, which is a different kind of stall. Oh, that's the other thing we need to watch out for is if we have no output, okay, let's say our aluminum scrap is backed up. We're not going to be consuming any alumina solution or coal. We're backed up. That backs up here. And these guys are going to be filled up. So if we have no place to put things, we'll stall the pipeline. And again, all of our fluid pipes are going to be filled up. But because of the valves here, we are not going to be pumping water all the way through to our buffer. So the buffer only buffers output from the aluminum scrap refinery. So in theory, in steady state, the amount of water in the buffer will fluctuate up and down. It's a lot more water than you can put in a pipe. These guys turn out 240 water per minute. So it's 2 cubic meters of water every half second. It's a pretty steady flow, but it does pulse. And it pulses by more than fits in the pipes. So in order to keep, we want it to keep flowing out steadily, so we provide this path that allows it to spew out. Now, we could probably use smaller fluid buffers, but I had some problems earlier. As I mentioned, these two require more than 600, together they require more than 600 water. Earlier, I actually had both of my water sources joining I had a VIP elsewhere that took my recycled water and merged it into the main pipeline, but that meant I only had 600 water to do the whole thing. And I was saying, why are things running slow? Why are things running slow? And it turns out it was because these pipes, these Mark II pipes, cannot carry enough water to feed both of those. Okay, and while I was debugging that, that's why I had the big buffers. So these big buffers could probably turn into little buffers. Let's see, those look like this. Drop one down here and we can compare it. A normal fluid buffer only stores 400. We're fluctuating around 200, 250. This rarely goes over 200. So it's possible that this design would be stable with a normal fluid buffer. I use an industrial here because I'm paranoid, and again, this is an experimental area. It might be that one fluid buffer hanging off of this refinery here is going to be enough space. I don't know. Anyway, so there we have how these three work. That was the big, hard part of the aluminum refinery. Once you've got that, once you've got these all set up so that they can handle stop and start, they can handle the fact that you can't rate limit to prevent deadlock. Now you have a nice steady source of aluminum scrap, which you can send onward. The other thing you have is silicon. Now, let's look at these guys. We're producing silica and alumina solution. Alumina solution is our main product. We have a silica byproduct. If the silica backs up, if we're not consuming this silica, this machine stops. So how did I handle that? Well, first of all, it's not enough silica for what we're going to do. Let's peek at this real quick. We're going to take this aluminum scrap and we're going to smelt it with silica. Ha! Here's where we use our silica into ingots. Now, if these guys turned out enough silica, these are going to be turning out 100 per minute each, so 200 per minute total. These guys require 150, and we've got 4 of them. So we need 600, so we need more silica. Okay, so now we have this other source of silica here. I'm going to be making silica, whatever silica I need. But it's the same problem as the fluid. If we back up over here, okay, this guy still keeps making silica, and it still will push it in, and no matter how carefully we have balanced things, okay, if we just kind of pick up everybody and merge it together, well, I can't say no matter how carefully, because there is a way we can do this. If we're not careful about how we balance things together, we can end up using all of this silica first, and instead of backing up into our quartz, we'll back up into here. So what do we have? We have 200 silica coming from here, so 100 and 100. We're going to bring them over to these splitters. Ignore the splitter for the moment. We're going to take 100 in here and 100 in here, and we're going to have enough coming in here to make up the rest of it. So this will attempt to take evenly from its 3 inputs. So how much did we need? We needed 600. So we need 100 from here and 100 from here, and it's going to get the other 400 from there. But the way the mergers work, it will preferentially want to balance. So it'll grab from here and here and here, and it gets the 100 and the 100 and the 100, and it needs more. So it takes it from wherever it can get it from. These two are going to drain. And then we're going to be taking as much from here as we want, but no more. So by carefully merging these in this way, so these are much lower, and because it's a low quantity, this works. However, notice I've got some spark splitters in here. The problem is startups, shutdowns, stalls. If our silicon is saturated and we don't have a way of relieving excess, these guys can't run. So even with this set up properly, if this silicon isn't moving, we still need to have a way for these guys to send some silica out. So smart splitters, where we send our overflow out here. And you notice that right now, nothing's moving, okay, because it's been sitting here stalled. So our overflow flowed out until this guy stopped up. And you know, so this guy is stalled because he has a full alumina output, but his silica is clear. So the moment we start drawing alumina, he'll start making silica. That's great. So here we are. We got all this going. Let's let it crank up. Now the way I'm going to let it crank up is I am going to empty our outputs. Okay, so now things are going to start to flow. So first of all, our end products start to move into the drone ports. So we start making more casings. And so very quickly, we are draining off our, well, that doesn't look right. Okay, so we're taking our ingot outputs, we're merging them together because this doesn't produce a whole ton of ingots. Going to merge them together into one belt, and we're going to take a split here, and I'm going to send a third of them off this way. Now, I could do a different kind of merge. I could do a split on each side and take a third of each side off that way, but that would only make a difference in this particular scenario where we suddenly started drawing. So it would only work until we ran out of buffered up ingots. Let's look at what happens when our amount of ingots in the in the foundries drops to 0. There we go. So very shortly we should see this drop off. There. Okay, we've got our backlog out. Now this is steady state. So steady state, we're just going to be flowing through. We're tucking away some ingots for people that need ingots, and there's not many of them. I think that the only use I have left for ingots now is making the empty canisters for nitrogen, and that's a closed loop system, so I'll need to make a few. And then we take 2/3 of each one, and it goes into, thank you, autosave, goes into these guys where we make aluminum casing, and notice how fast these casings are building up. That's great. Let's head back to where we are here. Here's our silicon running at steady state. Now, I didn't look, but I probably would have noticed a spurt of silicon coming out here, so we didn't get anything going out to our overflow. So, very shortly we should saturate. Let's do that by explicitly putting all of our casings back that we can, and all of our beams back that we can. So our drone ports are now saturated. What I'm watching for is as our saturation comes up at us from the right. There we go. Why is this guy still feeding in? I thought oh, I guess he had to do the last one. Okay. So as our saturation creeps back toward the refineries here, notice we filled him, so all of our ingots are now going to these guys, and these guys are filling up quickly. Notice I'm using a even split rather than a manifold. If I compact this down into one building, I will probably use a manifold. But the even split allows me to ramp things up and down quicker when I'm experimenting. I don't have to wait for one machine to fill before the other machines produce. It takes just as long for it to saturate like this, because that's all a numbers game. Ooh, there goes the drone to go get more stuff. Yeah, I hadn't timed how long it takes for this to saturate, and while we're waiting for that, let's color some things here real quick. Still not saturated. My color scheme is not well developed, but I do like to keep the pipes for the water distinct from the pipes for the Alumina Solution. These foundries can suck up a whole lot of stuff. Oh, the splitters feeding the foundries, these are all priority splitters, smart splitters. So if I wanted to, I could tap off at the end and send it to a sink to keep these lines moving. And it turns out that once these guys were working properly, I no longer needed to do that. But that option is still there in the experimental. Again, for a packed up factory, changes, I might use manifolds. I probably won't have an export of the bars, or if I do, it'll be kind of off to the side, tapped off of one of these, because it's, meh. Rare. Once I get all of my nitrogen loops set up elsewhere, this guy can go away, because I'll never ever have to make any more nitrogen bottles, because typical nitrogen loops might use a couple hundred or maybe 1,000. I don't know. I think I've gone hog wild on the nitrogen loops at this point, but the guys flying back and forth never seem to move more than a couple hundred at a time. So as long as you've got it, you're okay, and they circulate perfectly. Just make sure that you don't have too many, or if you have too many, your drone may not be able to unload and continue the loop. So again, big and deadlock. I'm just killing time right now waiting for this thing to saturate. Yeah, these self buffers here do take a while. Let's see, 120 per minute. Supposedly, this should be filling up in under a minute. Okay, so silicon is now starting to stutter. We're no longer accepting silicon at peak rate. And it looks to me like the aluminum scrap is also slowing. Oh, here, this is saturated here. So the more scrap output, and he's stalled, so he's not consuming anything else. So if this sent any silicon out, I didn't see it. So we apparently get a clean shutdown to where we stop producing before this saturates. That doesn't make any... I probably should put a container in at some point and measure just exactly how much silicon we leak each time we stall. Anyway, there we have it. The factory has gone through a restart cycle where the output is enabled. What if one of our inputs is stalled? I think I can do that by... what if all of our inputs are stalled? Let's go ahead and chop our bauxite inputs. And I'm going to let the factory run again for a bit. And we're going to see what happens when we restart after a bauxite stall. We need to be carrying less stuff here. Okay, so open that out, and open that out. And this should drain our self buffers of bauxite. So our question here is, what happens when we come to steady state here with no bauxite inputs, and then we suddenly get all of our bauxite coming in? How do we restart? And how much do we end up with in our fluid buffers? Do those go wild? Do we end up sending a lot of silicon out for recycling? So yeah, we're going to wait here until these guys stop. So in this case, it depends on what our buffers are, but if things aren't lined up perfectly, we may have more scrap in the buffers than we have silicon in the buffers, in which case these guys will fill in whatever silicon is needed. And if we have more silicon, then we run out of scrap. Any remaining silicon coming from these guys will get routed to the outputs. Let's watch the sink lines. Tappity tap, tappity tap. Sip of coffee. Okay, so we have run out of scrap, and I didn't see any silicon routing out, so which means that we used up all the silicon from these guys before we used up all the scrap from here. That's actually pretty good. That means I'm not wasting. So it may very well be that in the final factory, I'm just going to route this line over to a box somewhere. Maybe a box that feeds back into the beginning here. I don't know. That might work. Just feed this back into the beginning of the line for the production here. It will take from it in combination with these two. Might be enough. So we may be able to dispense with the sinks. That'll take some experimentation. So we're still running our foundries. Oh, aluminum scrap has big stacks. Okay. Well, that explains it. So these guys can build up a lot of aluminum scrap in their outputs. We buffer a lot of aluminum scrap here in the foundries. So it looks like the small amount of silica is probably not going to ever give us a deadlock. So in the final form, I am feeling more and more safe about taking these overflows and routing them back in here. Kind of as a original input to drain me. Or if we wanted to get fancy, I could have multiple instances of this. So we priority split these guys and merge them in here. And we take the outputs of them, we have another priority split that takes these guys and merges it in here. And then we take that out, that overflow, and we do that a bunch of times. It's not exactly a priority merge, but each one you do, you're getting a higher and higher fraction of your input guaranteed to go through, and a lower and lower fraction that might fall out. And eventually you just take the rest of it and jam it in the beginning, and you just kind of shrug and maybe put a box in as a buffer in case there's more, or at least so you can watch what the difference is. Is it stopped? It's stopped. Okay. So let's turn our bauxite back on. Everything here should be Cat 5. Again, in the final form where we compact this through, I am thinking about whether I want to use smaller belts and so on. Certainly in this save where I've got as many resources as I want, it's not a problem. But it may be that in a factory that's not doing free builds, that the cost of the category 5 belts and and lifts may be problematic. So in the final factory, we'll take a look at what the rates are on each one, and maybe I'll use lower marks, Mark 3s, Mark 2s, maybe even a Mark 1 if we have some slow stuff. Also, as we pack this together, we may have an opportunity to build bigger. Each one of these guys is doing 200 or 300 per minute rate. Currently, we are showing 273 here. Okay, so yeah, 2 to 300 per minute through each drone port. If the sources are farther away, they'll go slower. Not a whole lot. Drones are pretty good for long distance at medium rates. And this is being driven by, I believe, 2 normal bauxite nodes and a pure node. Just kind of streaming it on through. So we started everybody up. And again, I didn't watch to see if we got silica. We probably didn't get any. We're certainly not getting a sustained amount of it. But it cranked right back up. So it's my belief that this particular form, I actually like the way it lays out in this orientation better. It shows you how we've got this is the opposite one that I looked at. Originally I was facing the other way. So we've got the pumped water coming in, feeding the first guy, rising up into a U-bend and preventing backflow to drop down to top up this end. We've got the aluminum scrap providing recycled water, which again is limited to going this way. We preferentially take the water from the right, we fill him from the water from the top, and we fill him. And if his bursts are more than can fit in the pipe, his water goes through this inverted U-bend into here. And he is still running between 200 and 300 cubic meters in storage. So we are still in a situation where I believe that the smaller fluid buffers would be enough. But we do need to make sure that we have one fluid buffer of that size for each aluminum scrap, because as we grow this, as we scale it up, the amount of water that needs to go in the slop area is going to change. So did I leave? Yeah, I left a bunch of this in my inventory. Let's saturate it up again. I hate to just waste resources, but resources are infinite, so it's not a big thing. Okay, and I think that's everything I wanted to cover for the aluminum factory. This means that we have this nice building here where we are turning out quite a lot. These guys are not going to be quite saturated. The percentage numbers are not going to help me right now. I believe I overclocked the foundries to handle slightly more input than we get steady state. Pretty sure this is going to be 480 per side. So it's going to be 320 per minute going into the drone ports here for the aluminum casing. I think my goal was over 500 per minute total, which I'm going to need for making these thingies here, whatever they're called. Anyway, it's the next frame up from the heavy frame. I haven't built them yet. I've been looking at the recipes, and I needed a bunch of aluminum casings for it, which is why I expanded here. I had a aluminum processing area here. I am starting to tear it down as I shift things over here. First of all was I used to be exporting aluminum sheets. Aluminum sheets are only, at this point, they're only used in heat sinks. And I've got an alternate heatsink recipe that uses aluminum casings and rubber. Currently, I'm not using a lot of rubber in my factory, but I have a good source of it thanks to my power plant, which produces plastic and rubber as a byproduct. So I went ahead and shifted over to using the heat exchangers that use rubber. So now I no longer use the sheets, and I actually ripped up the sheet line, which came from these guys. I had 8 assemblers building sheets. The layout originally had 10, and I turned on some casings because I needed them. Well, now I've got all the casings I want over here. Perhaps I don't need the casings from this guy. That's my next step, is to start weeding this guy out. I want to eliminate these two. This guy back here is going to be harder to eliminate. I'll reduce him out so he will import his aluminum processing from elsewhere. But this is batteries. Batteries are painful. So the thing is, I believe batteries need aluminum ingots as their aluminum-derived product. So he's produced this solution. Where does it go? Where does it go? Where does it go? No! This guy uses Alumina Solution, so I'm not going to be able to touch this. This is a battery layout that I grabbed from someone online. Oh, gosh. Total Eclipse, I think? Anyway, one of the guys does really good layouts, and I've been studying it, trying to reduce it. And I thought it used the ingots, but I guess it uses the solution to make batteries. Which means that this Again, I have had to tweak this a bit because, again, he has water, and I've got all sorts of gimcrackery in here, and I've had to flush buffers and so on to get it to work because it kept stalling. Currently, I believe I am drawing batteries from this faster than it's... No, I'm not. I'm not. I'm backed up on the batteries. So this still has potential deadlocks. I may have Oh, I think... So I haven't touched this since I got the VIP, but I think the way that I happen to have brought my water in forms a VIP. Thank you, autosave. So we've got the recycled water coming in here with a fluid buffer and a pump and a one-way valve. You can see I haven't revisited this in a while. This is still, I was just tinkering it together until it worked. It wasn't quite working and kept not quite working. But I finally got this set up, and son of a gun, this is a VIP. And the overflow comes from this direction. And again, I was tinkering, and how do I split this? So I brought this guy up high and split him, and son of a gun, that's a VIP. So we have this refinery, and his recycled output is coming through here, where he is taken in preference to here. So we've got a fill-in water coming from here, but he has priority. But he's coming in as second priority, so first priority is the blenders. Second priority is here. So second priority is this refinery, and third priority is taking from this fill-in, which is currently not flowing. Well, we're stalled, so nothing's going to flow. He also provides fill-in here. So our main water comes in here, feeds these, and then there's a fill-in at the end, because I believe these are 180, and 180 is 360, and 180 is 540. So 540 and 90 gets us 630. So this pipe, Glenmark one. Okay, that's enough. If we tried to jam all of our inputs together, it wouldn't work. So we need to have 30 coming in from elsewhere. That's where this comes in. So 30 comes this way, and this fills in whatever it needs. So just by chance, this battery area is now working properly and has been tinkered with it until it worked. So you'll notice again, this fluid buffer is sitting between 1 and 200 cubic meters of water. So if I had noticed that this was working properly and studied it enough, I would have understood VIPs before I went to look at the web. Anyway, so this is working, and at this point, I'm pretty sure that I'm not going to touch it. I'm going to leave this making batteries for me, because it is making 20 by 6, 120 batteries per minute. My typical drones are using 1.7, 1.8 batteries per minute there. So let's say if I'm using 3 batteries per minute per drone, I've got a whole ton of drones, but that would be 120 divided by 3, 40 drones. So 40 drones in flight at once. That's a whole lot of battery. We can build more of them. I think if I had to build more, I would see if I could compress this into a building where the refineries were at the top. That's a lot of refineries. 6. That's 11 refineries total. So it would be a fairly large building, but I think I could do a multi-floor thing that would be a little more compact, or I could just leave it spread out. Anyway, I'm nattering. The aluminum is working, and we're slowly replacing my other aluminum with it. And let's leave a parting shot of the tricky bit, which is the water routing, with feedback. And if anybody skipped to the end, we have the pumped water coming in here, feeding the first refinery, and then coming through a backflow pipe, so we're preventing backflow. And this water will serve to top off what is here. We have this refinery, which is making aluminum scrap and producing some recycled water, which flows through as the primary stream to fill in the second refinery. It's not going to be enough. We fill it in here. That brings it up to maximum. The anti-backflow valves control where the water goes. So only my recycled water goes through here and gets buffered. So as we get our surge of water coming out as it runs, it will surge into the buffer, and then it will flow back out at whatever rate we need to keep this guy done. The other one is the same layout, but it is contorted around because the pipelines are on the opposite side here, which means this guy is closer to here than he was. But let's leave the parting shot with that one. Go back to photo mode, and here we are. Let's zoom out just a little bit. And there we have it. And that's an aluminum factory. And I'll do another stream the next time I have a factory that was a particularly challenging or interesting layout.